This is lecture 25, chapter 8, talking about friction. We've talked about friction to some degree in your physics 144 class if you took it at Poly, and we're going to extend a little bit on this. And essentially, we're going to focus just on static friction, statics. We'll mention a little bit about kinetic friction also. And this basic information you should is important because you're going to carry it through when you take dynamics, if you take dynamics. But otherwise, it's good to have some fundamental understanding of it. So let's start with what is friction? And the fundamental question I generally ask in class is it a friend or is it a foe? It's kind of like fire. Fire is a useful tool if you're trying to have a nice campfire, you're trying to cook something, but it can also, unchecked, it can burn your house down and cause a forest fire. And so friction is kind of the same way. If you're going to have any kind of motion, generally you have to have friction in order for that motion to occur. Your car wouldn't go anywhere if the tires didn't have traction or friction between the road and the tire. And you probably experienced this if you've ever driven in snow when a lack of friction causes a pucker moment, so to speak. So if you're climbing a mountain, surfing a wave, brakes on your bicycle car, all these are examples of how friction keeps you in the place you want to be. Even as something simple as a nail, nails are held together in wood by friction forces. Now on the flip side though, friction is very expensive. Some estimates put it at 1% of the general gross national product of the country in terms of cost, and that includes the energy to overcome it. So if you think about an automobile, for example, there's a fair amount of friction within the automobile, and so all of that is loss of efficiency from your motor through your back wheels. And the other thing about not just the energy, but is also the replacement of parts that wear out. So friction generally causes wear, or that's the source of wear, because friction is involved with two surfaces sliding past one another, and so generally materials break down after a while. Now, there's a lot to be said about friction. I spent a lot of time in graduate school studying this, but I'm not even going to scratch the surface, no pun intended, on this one. I just want to give you a little background so you know exactly what it is. So this picture is out of your book, shows you the different aspects of friction within a car. I think the most obvious would be your brakes. I like the picture of the engine they show here. On the left side, that looks like that's a little radio controlled RC engine, little two-stroke engine. Interesting they put that in a car, but if you look at the basics, the tire, the belts, the brakes and whatnot. So I think from a standpoint of understanding what friction is, I think we all have an experience and know what it is. And so how do we actually solve problems or calculate answers? So before we jump into that though, to have some idea of where friction comes from, you think of two surfaces that are in contact, they're never really truly in 100% contact. So if you have a book sitting on a table or a piece of wood sitting on another piece of wood, or anything, any hard, real engineering surface, you're only going to have about 1% of the contact area is compared to the observed area is actually in physical contact. And that has to do with the natural surface roughness that exists on all surfaces. Even surfaces that are highly polished still have a fractal pattern of roughness. The scale might be different. The distance between peaks and valleys might be a matter of nanometers. But as far as the distribution of peaks and valleys, it turns out that whether you're looking at something under atomic force microscope or the coastline of a country, the pattern of the valleys is very similar. So it's an interesting idea. But what does this really have to do with friction is that when two surfaces come into contact and you press them both together, then there's a tendency for those two high points to plastically deform. Because if you think about stress as force over area, you have a very small area and the contact forces become very high and cause a high stress that causes the two materials to deform. And so now when they deform, they have a tendency to lock together. And so that so when you start to push and try to move two surfaces apart, it takes more energy to break the surfaces apart than it does to keep them sliding once you've broken them apart. So a good example is that if you're trying to push a box across the floor, you'll notice that to get the box initially moving takes effort, but once it's moving, it's easier to keep it going than it was to originally start. And that has to do with this idea of the asperities on either side wanting to make contact. And all asperities are the high points. And so there's a lot of study into just this area of the materials where they come together in terms of surface chemistry, but it's still not completely well understood. I mean, there's some theories and some research, but overall I'd say it's still pretty speculative. Now, for something that's on Earth, and the advantage to being on Earth is that, with the exception of very few metals, that the exception of the noble metals, oxides tend to form on surfaces, and these oxides actually form a natural lubricating layer between two opposing surfaces. So, if I were to take two pieces of metal, say titanium, steel, stainless steel, whatever, and I were to put them together in a vacuum, they would actually stick together, and the force required to take them apart or pull them apart would be really, really large. In fact, it would make the coefficient of friction appear to be a number as high as 100, and we'll discuss that shortly, what that means. But it loses its physical meaning in vacuum. So typically on the Earth, though, because you have the oxide layer and you also have all these absorbed gases and just junk, basically, organic materials, oils from your hand, just organics, those help to prevent the two surfaces from really contacting metal on metal and essentially cold welding to one another. So an example of this was the Galileo high gain antenna, and this one was launched into orbit by the shuttle Atlantis back in 1989. It had originally been scheduled to be launched sooner, but because of the Challenger blowing up in 1986, it put kind of a moratorium on shuttle missions. And the way the high gain antenna operated, think of it as an umbrella, so that once the satellite was deployed, it was going to open up like an umbrella, and that would allow for images to be more efficiently beamed back to Earth. And so this actually traveled to Jupiter and beyond and took some really high-res pictures of Jupiter and its moons. Unfortunately, because the unit itself, it was built at Jet Propulsion Lab down in Pasadena, and it traveled to Florida and back several times. I've read 3 or 4 times, but as a result, the solid lubricants that are used in it became, essentially, they didn't really drought per se, but they became fractured, and they didn't operate as designed. And that's a whole other detail, but you can't use liquid lubricants in space, obviously, because they'll just evaporate. So they use what are called dichalcogenides, which are, they're a metal and a sulfur, like molybdenum, and graphite's another example of it. But they'll use these in space because they'll maintain their lubricating properties even in the absence of any air. So unfortunately, the lubricant failed miserably, and when they went to open it up, it was unable to open, and so they had to do some EE black magic to try to make the antenna as useful as possible. So just one example of how friction can ruin your whole day, and truth is stranger than friction. And here's a picture of it. So the picture left is at JPL, how all their satellites are built in clean rooms, or at least anything they launch from there. I've seen this location because I've worked there a couple times over the summer. Pretty interesting place. If you ever get a chance to do a internship there, I'd highly recommend it. Anyway, so here you have your satellite, and there's a lot more information I could say about this, but I don't want to get into the lecture. But if you're interested, you can look it up. It's a very interesting study in material failure. Okay, now we're here to static friction. So, as you may remember from physics, you start off with just a simple block sitting on a surface. We know that the normal force is just going to be equal to the weight, or essentially whatever the reaction is of the surface to the block. So if we were to push down on the block with something besides the weight, that would add to the normal force. We also know that if you were to apply a force P pushing the block to the right, and assuming the surface had friction, it's not a frictionless surface, then the friction would match 1-for-1 with the applied load. So if I apply 1 Newton to the right, the friction force is going to be 1 Newton to the left. If I apply 2 Newtons to the right, it's going to be 2 Newtons to the left. And so it'll match 1-for-1 until I reach the maximum friction coefficient, or the maximum friction force. So the friction max is defined as the coefficient of static friction multiplied by the normal force. Another way to say that is if you were to take the force required to break free and divide that by the normal force, that would give you your mu static. And so once you reach that point, you'll be in this transition mode where the material will start to, or the block will start to slide. So if we think of it from a starting point, if we apply P when it's vertical, it's just going to be added to the normal force. So in this example, we have no sliding friction or no friction at all because there's no lateral force. This is in the first situation. In the second situation, we're applying P at an angle. So we have the y component of P is going to be added to the normal force. And that's why we say normal force is equal to Py plus W. And then we also have the weight. But at this point, we haven't created enough force to overcome the mu static times the normal force. So until we reach that point, we aren't going to go anywhere. And then we get to the third stage, which is where we're just about at impending motion, and that would be where the x component of P is equal to the mu static times normal. So when you say equal to, mathematically that's easy to see, but in reality it doesn't just go from not moving to moving. There's kind of this stiction transition, and that transition is difficult to measure in real life because, as you can imagine, the asperities, the peaks and valleys of your surfaces are locking, unlocking, locking, unlocking. And so from a measurement standpoint, it's kind of a rough area, and then you get the release, and then the material starts to move. And that's what we have in the last case, where you have motion. And so at that point, the friction force drops because your kinetic coefficient of static friction, UK, is generally always less than mu static. So that means it requires less force to keep it moving than it did before. So if we look at this as a curve, we can see that force versus load, friction force versus load, is that it's a 1-to-1 ratio roughly until we reach that maximum. And then they have a nice smooth line dropping, and then you continue forever with kinetic friction. So it's not quite as pretty as that, but that's a good model to look at when we're first learning it. All right, so let's talk about static friction in a simple example. And I picked this example because we have an object on a block, and it has a mass of 50 pounds, and then we can apply a value P to it however much we want. And we can see that unlike our other problems that we've done in this class, there's usually one way to solve them, or maybe a couple ways. You can use a force triangle, or you can sum moments. But there's usually a situation, one defined situation, or one defined outcome, or we're finding a moment, we're finding a result, we're finding force. In this case, friction is a little more tricky because we have multiple things that can happen in the situation. So if you picture it, if I apply a force P, then if my P force is great enough, that block is going to slide up the incline. If my P force is not enough, let's say there was no P force, then most likely that block is just going to slide down. Or you have a region where a range of P values where the block will just stay put. So there's enough to keep it from sliding down, but not enough to start it sliding up. And that becomes the tricky part of figuring what that is. So let's look at some different situations. So here's our drawing. We have mu static and mu kinetic, 0.4, 0.3, respectively, and then we have this load. So here we have this redrawn, and so I have my load P. I have this whole angle's 40 or 10 degrees to the horizontal, and then I have my 50-pound load here, and the block can move up the ramp, block stays static, block slides down the ramp. So what are my situations? So let's try something first. Let's say if we didn't have anything, let's say we just started with no load whatsoever, let's just say P was 0, then what would happen? Let's go ahead and draw that free body diagram and see what that would look like. So here, if we have no P whatsoever, then what I've done is I've tilted the axes, and if I do that, this is 30 degrees here, and we have friction force, of course, is going up the ramp because if it wants to slide down, friction is going to oppose it. If N is going up this way, then that's going to be, of course, normal to the surface. So we can kind of see that from this drawing that the force, if we sum the forces in the x direction to 0, then we know that 50 sine 30 is 25, right? So 50 sine 30 has to equal the friction force, right? So the friction force in this case equals 25 pounds. Now, what that means is when I say the friction force, that's how much force I have to have in friction in order for this to not move. So the way I want to write this then is this is the force required for equilibrium, because anything more than that, then it's going to move. So that means the question then is, do I generate that much friction force, right? Now, the friction force, the only time I can really know what the friction force is looking at what's opposing it. And so right now, I know there's 25 pounds of force wanting to slide down. So in order for it to stay still, I have to have 25 pounds going up. But how much friction do I really have? Well, I know that my maximum friction, so F max, is going to be equal to the static coefficient times the normal force. So if I look at this, I say, well, what is my normal force? Well, I can see that if I sum the forces in the y to 0, then normal force is what? It's going to be equal to 50 cosine 30 equals normal force, right? So I could have said normal force minus 50 cosine 30 equals 0, but I think we understand that's all there is in that direction. So 50 cosine 30 gives me a value of what? So that's 43.3. So I know my normal force is equal to 43.3. And so therefore, my friction max is equal to what? It's equal to 0.4, because that was my given friction coefficient, times 43.3. And so that gives me 17.3. So the block is going to slide because I'm told here that I have 17.3 pounds of friction force available. That's the maximum. But I have 25 pounds of force. So it means it's going to slide. So then the next question is, well, we could apply a force P as we did here. And you could say, well, what happens if I apply a force of 100 pounds? What happens if I apply a force of 80 pounds, of 50 pounds, so forth. So we know that at some point, our force is going to be great enough that it's going to slide. We know that at some point, the force is going to be great enough that it doesn't slide up, but it doesn't slide down either. It holds it in place. So the question then is, where is that point? How do we figure that out? So it'd be nice to know if I'm going to apply a force P, how much can I apply, or where is that kind of sweet spot? So that's where we can actually solve. What we can do is we can look at it, because we know that I could have gone, so I could have said, calculate, if I gave you 100 pounds, you could have gone ahead and applied a force P here at 40 degrees and 100 pounds. And you could have gone ahead and had these, and you could have changed this all, right? Because you know that if I put 100 pounds here, that meant my normal force would have been 25 plus the sine of 40 times 100. So it increased n, it would increase the maximum friction, but then I would have had the cosine of 40 times 100 moving up the ramp also. And the other thing is that this would have changed. So maybe, it's probably worth running through that just so that we're all on the same page. So if I go ahead, let me draw that real quick. So let's go ahead and do that problem. So here we have 100 pounds. We know that whole thing is 40 degrees from here down, because this was 10 right here. So I've drawn that. I've tilted the axes for ease. Normal force is still there. So let's go ahead, just like we would normally do a problem. So the math itself is not difficult. It's just like before. It's just understanding how to apply it. So sum of the forces in the x to 0. And we have the friction force. Now, of course, the friction force has switched sides because now we're assuming that we're going to push it up the hill. And so the answer comes out. So if I've assumed something wrong, it'll tell me, and I'll show you that. So I have my friction force is going to the right, plus 50 sine 30, also going to the right, minus 100 cosine 40 equals 0. All right, so if I solve, I get a friction force equal to 51.6 pounds. So what this represents is this is how great a friction force I need so that this applied P cannot push the block up the hill or up the ramp. So now I have to look at how much friction force do I have, right? Because I need to know, I want to know that my friction max, is it greater than 51.6 pounds? That means no motion. If F max is less than 51.6 pounds, then I have motion. All right. And so I know that F max equals mu static times n. So really, if I solve for n, I know this is 0.4, then I can determine that. So go ahead, I sum the forces in the y direction to 0. And I know that I have n going up minus 50 cosine 30. And that's also minus 100 sine 40. And that equals 0. So I get n equal to 107.8. And so my F max is equal to 0.4 times 107.8. Sorry. and that's going to equal 43.03. So what did I say? My F max is 43.03. It's going to be less than that. And so because the maximum friction I have available is only a function of n times mu, if I want to increase the friction, I either have to increase n or I have to make the surface rougher. That's essentially what the coefficient is. So I know it's going to slide. So it's going to slide at 100. Now, I could go ahead and plug in 90 and then maybe 85 and down. And at some point, like I said, I'm going to get to a point where this is going to be no longer able to push it up and I'm going to be in equilibrium. It's not going to matter. So I could do it. I could go 90 and then 85. I could go to 80 and then maybe or 75. Maybe I found I went too far and it moves, and then I could iterate back and forth until I got exactly there. And that would be fine. That's one way to do it, but that's kind of tedious. Or I could just set up an equation set and solve for it. So if that's the case, looking at this same setup here, so let me do this. We know what we're going to do now is we're going to want to find P. So we are in equilibrium. All right, so we're going to find P so that it doesn't go anywhere. Now this is just one facet of it, because what we'll find is let's just do this one first and I'll explain. So again, we have our so we're assuming, again, we have our free body diagram here, and we're assuming we're going to go up the hill. So we have friction opposing that. So what we can do then is, again, we're going to define what is our friction force. So we'll go ahead and say our friction force is equal to what? It's equal to P cosine 40 degrees minus 50 sine 30 degrees. So that's what our friction force is, isn't it? Because I just had friction force, and that would be so that these are equal, right? We're saying we want them equal. So we want our friction force equal to whatever force is there. So that's going to be P minus that. And then we know that F max, friction force max, is going to equal mu static times N. So let's figure out what is N. So first we're going to say F max divided by 0.4 equals N. Okay. So now I know that. So let's go ahead and fill in what N is. So N in this case is 50 cosine 30 plus P sine 40. So if I do that, maybe that's easier to see. So we know that N equals this, but N also equals this. And that's why I did this, because what I'm trying to do is I want to be able to set these equal and solve. So I know that my F max over 0.4 is equal to 50 cosine 30 plus P sine 40. That's just looking at it from 3 by diagram. So I multiply both sides, I get F max equal to 0.4 times 50 sine 30 plus 0.4 times P sine 40. Sorry. So if I do that, this ends up being 20 cosine 30. Sorry about that. This is cosine 30. So 20 cosine 30. That's just 0.4 times 50. and then plus 0.4 p sine 40. So now what I'm going to do is I'm going to set equal this and this, right? Because I know that we want those equal to that, because that's going to allow me to solve for my one unknown P, where the friction created by the normal force is equal to the friction, my maximum friction created. Now, the thing that makes this problem a little more difficult is that normal force isn't a constant. As we make P bigger, N is going to get bigger, which subsequently means the friction force is going to get bigger. And so we can't just hold it as a constant. So if we set those equal, we end up with this. And let me go ahead and just draw it real quick. Okay, so here it is written out. So we have P cosine 40 minus 50 pounds sine 30 equals 20 cosine 30 plus 0.4 P sine 40. So this is essentially setting the friction force max. And if we solve, we know that's a number and that's a number. So we move those both to the other side and we move this back to this side. We get P cosine 40 minus 0.4 sine 40P, factor out the P, make these numbers, solve, we get 83.155 pounds. So that tells me that at that point, the 83.155 pounds, if I'm applying on this, anything more than that, it's going to slide, anything less, it's not. Now, what we haven't figured out is how much less before it starts to slide. We showed that if P is 0, that's not going to be the case. But where's the lower threshold? And so there's a certain amount of P that we'd have to apply such that this is still held up. And so we could do that too. We would have to rewrite these set of equations. The only difference is we would now need to move friction to the other side. And that's what's weird about friction, is it's always opposing motion. So if we think we're going to slide down, we're going to change it so that the friction points the other direction. And then we'd set up these equations the same way, only with friction pointing up, and then we would subsequently solve. Now, it turns out that that you could have solved this whole thing with a forced triangle. And that's something I want to mention real quick, this idea of what's called an angle of repose. Now, I'm not going to really dig too deep into it, but it is an alternative way to solve some problems. Now, where it comes from is that, remember, we have a block. Let's say we know it has a certain weight, so therefore it has a certain normal force. And again, we're drawing with single vectors, is just meaning, we don't care about where they contact. But in this case, we're just going to say, I've moved it over here so that I can illustrate this. Now we know that this is going to be your friction here, right? Your friction force. So what if I were to take the normal force and the friction force and combine it into one? So let's say I did this. So now I have something like that. So instead of the traditional normal force and friction force, I have this, and with respect to the horizontal, I have that, and I call that R. Because R, really, what does it equal? It equals, if you add this and this, you get that. So this angle here then is called phi, or the angle of repose. And it turns out that, and through a simple derivation, which is in the book, I want to show you, that if you take the tangent of phi, you get mu static. Or on the other hand, if you take the inverse tangent of mu static, you get phi. And so just this simple relationship, and it makes sense because if I take the tangent of 45 degrees, what do I get? I get 1. Well, that makes sense because if this was 45 degrees, it would mean that my normal force and my friction force were the same, and which would mean that if I said friction force divided by normal force equals 1, right? So the math works out. because 45 degrees would be these are both equal. And essentially, for our purposes, you can't have this ratio be greater than 1. Now, it turns out that this number could actually be 100 in a vacuum, but it loses its physical meaning. So for us, friction, this ratio of friction force over normal force, which gives us mu static, is always going to be a number less than 1. Okay, so 1 or below, generally less than 1. So that's your kind of idea of angle of repose. So it turns out that we could have, trying to figure out our what our p-value was, we could have taken this 50, we could have combined the normal force and the friction force, and we knew this angle because it's just the inverse tangent of 0.4. And if we did the trig real quick, we would have gotten this triangle where this would have been, internal angle would have been 15 minus phi, this would have been 30 plus phi, this angle here ended up being 110 degrees. And so if you went through and took the time to do it, you could see it. But what it would allow you to do then is just quickly do a, using the law of sines, you could have quickly found what P was, all right? So I'm not going to do the problem, but it is in one of the examples in the book, in first couple examples in the problem set. So I know most of you probably have the solution to manual, you can see it. I think it's problem 8.5. But the point is that the force triangle can come back and help you in this. I'm not going to spend a lot of time on it because I want to get you guys ready for the final. Now, the final is going to deal with a single friction problem, among other things, but there will be a friction problem on there. And the type of problem that'll be on there is most likely going to be something where you're going to have to determine if something, at what point something starts to move based on the load applied to it and the friction that is the friction that it creates. So one of the things about these problems is there's a lot of substitution. And the reason for that is because we know that in general, that anytime we have a object that we have the normal force and we have the friction force. And so some of the forces in the X, forces in the Y, but we know that these are related by mu static. And so we're going to use that fact to solve. So let's go back to here. And so we could have done more with P, but I think you got the point of that. So let's look at this example. Now, this is on the previous problem, and this is on worksheet 24. And so I want to do this problem, and then that'll be it for this lecture. And then I'm going to do another lecture with more examples of friction. So I know I went through quickly a little things. Now, one final comment about the angle of repose is that you don't have to use it. It's just like force triangles, you don't have to use them. If it convolutes things, don't worry about it. It's just something in the back of your head. If you feel comfortable with trig, it can make things a lot easier. For example, in that problem where I derived the setting the two equations equal, that wasn't very tough, but if I used the force triangle, it was done in just a few minutes. But again, it's how comfortable you're with trig. All right, so let's look at this problem. So here, what we have is a 200-pound pipe, half section, sitting, and you have this cable at A, and then you have this tension pulling it up. And so what we want to know is how much tension or what force do we have to put on it before this thing's going to tip over or slide. So those are the two options, as you can imagine. So if I'm pulling it and the angle is 30 degrees where alpha is defined, then as I pull on it, the thing's either going to want to tip at B or it's going to want to slide along A and B. So you can picture, in one extreme, if the tension were running along the x-axis to the right, then there'd be no there'd be no moment because it would be at A, so therefore it'd have to slide. Whereas if we put the tension completely vertical, then there'd be no way it could slide, it'd have to tip. So there's some angle, some point where T is going to cause it to tip, or it's going to slide. We just don't know what it's going to do. And we're not really asked to find where that point is of tippage. We could, but rather what we're going to do is we're going to find where does it start to move. And once we know where it starts to move, then we're going to say, then we can determine, is it slipping or is it tipping? Okay, so let's go ahead and draw that. All right, so here we have our, so notice there are no dimensions given it, so probably means that there's none, that we don't care about them. But if you're in a, if that bothers you, you can always pick the radius equals 1, in which case it will drop out. So in this case, so we have our free body diagram. We know that tension is coming up here. We know that if we draw, since that's coming off at a 30-degree angle, and we draw a line from the center to the tangent, that has to be 60 degrees because it's going to be 90 here. So that's just geometry. We know that the normal force A, normal force B are going to be at contact each of these points here, and the friction is going to be going that way because we want to move to the right, so it's going to oppose. So if you're not sure how to start, then I'd say is look at the problem and what are we trying to find? We're trying to find T. So first thing, just like before, sum the forces in the X, sum the forces in the Y. And I'm not saying that all the problems are just simply do that, but for the most part, if you just start off with that idea, looking at what you want to find, and then eliminating the unknowns, then that seems to work pretty well in most of the friction type problems. And I have put an assignment up on this, and I would recommend looking it over because that is going to help you on the final, being familiar with this. So we sum the forces in the Y to start. So we do that, and what do we have? We have NA plus NB, so normal force at A and B, minus the 200 pounds coming down, and then but plus T sine 30. So whatever T is, sine 30 is going up, that equals 0. So we can solve NA plus NB, and that's going to equal 200 minus 0.5 T. So we have that now. So there's an equation, we'll come back to that. Now, we also know that for this thing to slide, that the friction A plus friction B is going to equal mu static times the normal force A plus mu static times the normal force B. Or another way is we can write it as 0.4 times NA plus NB. And that's going to equal FA plus FB. So notice that I've drawn this NA plus NB. I also know that this up here equals, this NA plus NB equals 200 minus 0.5 T. So this is probably going to be useful soon, because remember what we're trying to do is we're trying to eliminate our variables, and so that we only have enough variables as we have equations. So we'll hold that thought for a moment, and then we will go ahead and sum the forces in the X. So if we sum the forces in the X to 0, notice that that will give us FA plus FB, and then that's going to be times FA plus FB times, wait, pause for, sorry about that, getting ahead of myself. So we notice that for some of the forces in X, we have T cosine 30 degrees, and then that's going to be minus FA minus FB equals 0. All right. So now let's hold that for there and come back to up here, which I probably should have done in the first place. So I know that I can substitute FA plus FB, FA plus FB equals 0.4 times 200 minus 0.5 T. So all I did was take this value and stick it down here and rewrite it. And that gives me 80 minus 0.2 T. And so that's what that is. Now, if I come back down to this value, what do I have? I can rewrite this as T cosine 30 degrees equals FA plus FB, right? And so, or another way to write it would just to be, say, T cosine 30 degrees equals 80 minus 0.2 T, all right? And so in that case, I can go ahead and solve for this. And as I solve for T, I get T equal to 75 pounds. So effectively, this ends up being T, and if I move this to the other side and then factor it out, it's cosine, actually, make it easier, square root of 3 over 2 plus 0.2 equals 80. And this is a number just a little bit bigger than 1, so 8T ends up being about 75.0 pounds. Okay? So that, again, and that's how a lot of the friction problems are done, though. But you'll notice how I didn't, nothing fancy. I just know that if it's going to move, and that's the caveat, is that unless you know it's on impending motion, you have no way of knowing what the friction is, because the friction can only be found when with mu times n when it's at a maximum. And so we assume that it's about to move, friction's at a maximum. We're able to then substitute as shown with between the normal force times mu and the friction force. All right, so hopefully that made sense. So now we have T is 75 pounds, but we're not done yet because we know that that's how much it's going to take, but we want to know, is that going to cause the item to tip over, or is that going to cause the item to slide? So let's look at what we have now quickly. Now we have T. We know that at this point here, T sine 30, and that there's going to be T cosine 30. Now this is A over here, and this is B. So it makes sense that if this thing's going to tip, it's going to rotate about B. So what we're going to want to do is we're going to want to sum the moments about B. Now, what would be the criteria for the fact that this thing has tipped? It would be that the normal force here is 0 or less than 0. Now, a normal force less than 0 has no physical meaning, but if that's the case, it means that essentially that this thing is no longer in contact with the ground, therefore we know it's tipping. If the normal force over here is greater than 0, we know that it's actually the whole item is sliding. So again, we still have our normal force A, normal force B. We have friction A, friction B. Now, sorry, it's a little sloppy, but let me go ahead and I'll leave those in there. So there's friction force A and friction force B. Now, if we think about distances, what do we have? We have this distance here we're going to call 1 radius. This distance here to here and to here, because we're going to need these for our moment. We know if that's 60, then this is going to be R sine 60, and this is going to be R cosine 60. All right, so that will give us our locations for this and this. So let's go ahead and sum the moments about B, 0. So with that, we know, now we know we still have the 200 pounds, of course. 200 right in the center. So we have 200 times R, because it's 200 pounds going that way around B. And what else do we have? We have the normal force. So 200 pounds times R minus normal force at A times 2R. And then minus T cosine 30 degrees. And its distance is going to be times R sine 60 degrees. And then that's going to be minus T sine 30 degrees. And what's its distance? It's the T sine is going to be R plus R cosine 60. So R plus R, sorry, it's getting messy right below it. R plus R cosine 60 degrees. All right. So there's that. And all of that has to equal 0. All right. So we have everything. We have the movement from this, and then A, and that's it. And of course, the weight. So the weight's the only thing keeping it. Everything else wants it to go the other direction. So we're going to go ahead and simplify this now. And if we do, we end up with 2 NA. Now, one thing you can see right away is that if the R cancels. We have R here, R here, R here, and R here. So all the R's can be divided out. That's why I said earlier it doesn't really matter. So now we have 2 times the normal force A is going to be equal to 200 minus, and I factored out the T, and it's going to be times cosine 30 sine 60 plus sine 30 plus sine 30 cosine 60. Okay, and that's our equation, and that's not equal to 0. So that's equal to 0. So here's our equation now. So we're almost done. We know that this is 75 here. We can plug in for that, and then we can look at all these values. Well, we know that the cosine of 30 is the square root of 3 over 2. The sine of 60 is also the square root of 3 over 2. The sine of 30 is a half, and that's a half, and that's a half. So what we end up with is 0.75 plus a half plus quarter. Okay, so what is that? That's essentially 1.5. So we solve, and we have 2 NA equals 200 minus 75 times 1.5. And NA ends up being 43.8 pounds. So the fact that it's not 43, it's 43. The fact that it's a value larger than 0 is all that matters. So we know that it slides, it doesn't tip. All right. Okay, so that's 2 types of problems. So I'm going to come back in the next lecture, talk a little bit more about friction problems and some examples. I'm going to mention wedges briefly, and then may have a third lecture. I'm not sure yet if we need it, but I'll have at least one more lecture on friction. So hope this made sense, and have a good day.